So welcome to this plenary session where we are going to hear fantastic results, fantastic experimental results. First by James Mott, who will going to tell us about the Muon G-2 exciting result, right? So James, the floor is yours. Before we start, I would like to remind all the participants basically to follow the code of conduct, right? And probably you cannot really speak up directly. So if you have any question, you can type it in the question and answer chat. We'll monitor them and we will take the question at the end of the talk. So James, the floor is yours.
Thank you, Christophe. Thank you for the invitation to come and speak. My name's James Mott. I'm from Fermilab and Boston University. And as Christophe told you, today I'm going to be primarily telling you about Muon G-2 from an experimental perspective. So we'll just start off by asking what is the G in G-2? Well, it determines the spin precession frequency in a magnetic field. So it basically couples the magnetic moment to the spin. So if you put this magnetic moment inside a magnetic field, you're going to have some torque, and it's going to cause the spin to precess around like this cartoon of a top here. Now, if the only thing we had in the universe was this one particular diagram, it's the only one we could draw, then just from the Dirac equation, then we find that this G is just exactly equal to 2. Okay, but obviously we know that there are other diagrams we could draw, and you put in these virtual loops and they basically alter the calculated value of G, so it becomes ever so slightly larger than 2, a kind of a part in 1,000. Now the X and Y here, they could be standard model particles, or they could be new physics particles, and they're all having an influence on this G value. Now, what's particularly nice about G is that it's something that we can predict from the standard model very precisely, but it's also a quantity that we can measure very precisely. So we make these two precision prediction and measurements, and we then compare them. And if they agree, fine. But if they don't, then it's sort of telling us there might be something in nature that isn't in the standard model. So this is the whole point in the experiment. Now we're going to need some standard model value to compare to. So where does that come from? Well, the one we use comes from a group called the Muon G-2 Theory Initiative. This is a consortium of over 100 theorists who get together. They started off back in 2017 here. Obviously, they've been working for many decades before, but this was kind of the birth of this group, and have had a couple of jollies since in a couple of years and continued virtually since then. And they come together and have come up with this white paper down here, which I've got a link for. And this basically compiles all the theoretical inputs and provides a recommended value for the prediction. So that's what we use to compare to. Now, what is the number? So there are kind of 5 main contributions to this number. It's kind of whole standard models in here if you look. So we started off with G just 2 from the Dirac equation. But then the quantity of interest, which is kind of where all these radiative corrections are coming in, is actually in this A mu, which is G-2/2. Right? That's all these terms here. Now it's completely dominated by the QED value. This 116 million number in this kind of unit is much bigger than these other numbers. But the uncertainty from QED is very small because we can calculate it, and indeed it's been calculated at 5th order. And where things get messy are these hadronic terms. And this is where the uncertainty is dominated. You can see it's kind of 40 and 18 compared to these other two small numbers here. And so this is where the majority of the work from the theory initiative is happening right now. So I'm now going to punt most of this theory stuff into Hartmut's talk, but I will just mention one thing to say that it's not 100% settled at the moment. There is some open questions here. In particular, the value that I'm using today from the theory white paper just comes from the data-driven approaches to calculating hadronic vacuum polarization. And so that's these 2 terms down here. These are kind of the ones that have been done historically. But more recently, we do have all these lattice QCD calculations shown here in blue. And one in particular that came out at the same time as our experimental result is getting down to kind of precision of sub%, which is starting to be able to compete with these data-driven versions. And there's some tension here. And so what I'm showing today is just the values from the white paper from the theory initiative. That's this value here with an uncertainty of 368 parts per billion. If you're more interested in these calculations, then I recommend you tune into Hartmut's talk at 2 o'clock today, he's going to be giving a mini review of the white paper and where all these numbers come from. So I encourage you to attend that. Okay, so before our result, how did the theory and the experiment comparison look? So it's a long-standing discrepancy, this one. We all know about it. So the previous best result came from Brookhaven. They had an experiment that ran around the turn of the millennium. And they ended up with a difference between the standard model and this standard model prediction and the old experimental result of 3.7 standard deviations. So the precision here is 540 parts per billion. The theory's gone past it here. And then you can just look versus year, kind of the theory estimate hasn't moved much with the caveat of the previous slide there. It's sitting here and this discrepancy is still there. Now, it's been around for 20 years, this discrepancy, and it's generated an awful lot of interest. It's remarkably constant, the number of papers it's generated, kind of 250 per year, and for 20 odd years here. And so the questions we're kind of asking ourselves here is this difference a sign of new physics? It's obviously what we're all hoping, but we do have to make sure it really is real before we get too carried away. In terms of the new physics stuff, so Bhupal will talk in 2 talks time about anomalies, and he'll cover this anomaly and possibilities for beyond the standard model physics. Of course, it could also be a mistake in the theory. Again, I point you to Hartmut's talk where he'll discuss the theory. So what I'm really trying to address today is, could this be a mistake or a statistical fluctuation in the Brookhaven experiment, which I think is motivation enough to say it's time for us to do this new experiment, which I'm telling you the result from today. Now, the new experiment, it's also called Muon G-2. There's 200 collaborators. Here's a picture of us in Washington. We come from 35 institutes in these 7 countries. We have a broad breadth of physicists from particle and nuclear, atomic and optic, accelerator and theory. And we need the expertise from all these different areas to do the experiment. Now, the experiment's based at Fermilab. So if those of you know Fermilab, here's the high rise and the cafeteria where all the important stuff happens is here. And we've got a good spot, not too far from the high rise over here on the Muon campus. G-2 is in this building over here. And then U2E makes up the other building in the Muon campus over here, the Tevatron ring over here and Chicago in the distance. So that's where we are spatially. To orientate you time-wise, this is kind of the experimental timeline. So it really got away in earnest in 2013, where things started happening. So the magnet was moved over from Brookhaven. I'm sure you've seen pictures of the big move. The building constructed in 2014. We had a period where we shimmed our magnet and made it uniform. A short commissioning run in 2017. And then the data I'm telling you about today is from a 3.5-month run in 2018, which we call run 1. It's a small fraction of the total data, only 6%. And the runs have continued since then, 1 per year. So we're in run 2, 3, and we're now in run 4 and still taking data. Now with this run 1, what uncertainties can we expect? So here's the precisions that we've got. So I'll remind you the Brookhaven precision was 540 parts per billion. This first result, which was released on April the 7th, has a precision of 462. So we're kind of 15% better than Brookhaven, even with this small fraction of our expected target. And then the final target, we're going to aim to get down by a factor of 3 or 4 from where we are at the moment and split it roughly equally between statistics and systematics. So, I mean, this whole big step down is statistics, basically. Okay, so how do you actually do this experiment? Well, we store longitudinally polarized muons in a ring with a vertical magnetic field. So if you do that, the muons are going to go round and around at the cyclotron frequency, and their spin is going to precess at the spin precession frequency given by Lamour precession here, and then a relativistic Thomas precession term here. Now, if you just imagine taking the difference between the spin and the cyclotron frequencies, and a world where G happened to be exactly equal to 2, what you'd find is that these 2 frequencies are the same, so the difference is 0. And if you injected your muon into the ring, it's going to go around and around here following the blue arrows. And the spin is just going to point exactly in the same direction all the time as the momentum, because it's got the same frequency. And so it'll always be pointing tangentially as you go around. Now, I told you before that G obviously isn't 2, or we wouldn't be doing this experiment. So the difference here then, once you take this through, you actually find that it's proportional to A mu, which is the kind of new physics thing we were interested in before, the radiative corrections, as G-2/2, and the magnetic field plus some constants. Now this means that the spin precession frequency is ever so slightly larger than the momentum, So as you go around here, the spin just creeps ahead of the momentum as it's going around. And if you imagine just being set on a detector here, what you would see is the spin pointing inwards towards you, and then a time later it'd be pointing outwards, and it's going to point inwards and outwards. And the frequency at which it's pointing in and out is this beat frequency, omega A. So this is the whole principle behind the experiment. We basically measure this spin precession frequency, and we measure the magnetic field, and then we take the ratio, and that allows us to get hold of A mu, the quantity of interest. Okay, so here are the ingredients we need. I'm just going to spend a few minutes talking through how we get them to make that ratio that I told you about, starting with this magnetic field map. So here's a picture that you've probably seen of the magnet and the experiment. What happens here, the muons, as far as we're concerned for this talk, magically appear. There's obviously a huge amount of work in the accelerator complex to deliver us this muon beam. They come down here and they go inside our magnet and start spinning around, rotating around here at the cyclotron frequency. Now, if you were to take a slice down, for example, this white line here and look in this direction, this is the cross section you'd see of the magnet. It's this C-shape yoke. We have a 1.5 Tesla field that runs vertically here, and the whole thing is 50 feet in diameter. Now, there's these superconducting coils here that generate the field, and we flow current through them like this. And if you squint and use your right hand rule, you can convince yourself you're going to get a field going around in this direction here. Now, these coils were moved over in 2013, whole from the Brookhaven experiment. And then at that point, we then underwent the shimming campaign, where we basically move like these wedges and these tiny pieces and the orientation of the poles to try and make the field in this region as uniform as possible. And in the end, we spent more effort on it than was done at Brookhaven and ended up with a uniformity 3 times better, which helps with systematics. Now, I say we're more uniform, we've got to be able to measure it to know that. So how do we do that measurement? Well, we have this trolley, this kind of elongated soda can. It lives in the vacuum and drives around every 3 days to map the field. And it maps it using these NMR probes. There's an array of 17 probes just behind this cap here. They're filled with petroleum jelly, and we measure the proton precession frequency inside there to estimate the field. So it's kind of a co-magnetometer technique. Now, you move the trolley around and you take field maps at 8,000 points around the azimuth of the ring, and you get maps that look like this. But what we really care about is the average around the ring. Obviously, a muon is going to be going through each of these field maps, and the field it sees is the average. So here's a typical example of an azimuthal average. And you can see that the variation here is less than 1 ppm around. It's small variation around the ring. It's nice and uniform, and especially here in the middle where the muons actually live, mostly in the middle of the aperture. Okay, so we obviously can't have the trolley in the ring while the muons are there, or they just smash into it and we lose them all. And so instead we take the trolley out and then we monitor the field during the data taking with these 378 fixed probes. So these are the same probes as the ones on the trolley, but they live above and below the vacuum chamber, as shown in this picture. And the idea here is you take a trolley run and measure the field, and then you remove the trolley and you track with these probes what the field's actually doing. And then at the end, you take another trolley run and you use that to anchor the interpolation. And you can see if you just drew a straight line here, you'd obviously miss these excursions. There's some day-night oscillation from temperature here as well. So we track all this and use that to get the right weighting for the magnetic field. Now, what we actually really want, instead of the precession frequency in terms of petroleum, is in water. So we have to transfer our calibration across, and we do that with this plunging probe. It's a cylinder of water, basically. We put that inside where the trolley normally lives, measure the field, take it out, and keep swapping places. So we put the trolley there and measure the field. And we swap back and forth many times and basically transfer the frequency calibration from these probes to this probe. Then we can take this probe out and take it over to an MRI magnet that we have at Argonne, and we use that to compare against this spherical probe, which has smaller systematics. And this is kind of really the gold standard for the field. We cross-check everything as well against this new probe that we developed with helium-3, and everything works, and this has got different systematics. So if you plug it all together, the final uncertainty from the calibration and the tracking and everything else with the field is 114 parts per billion. And so it's much smaller than statistical uncertainty at this stage. Okay, so the second ingredient we actually need is the muon distribution. It's no use having this map if you don't know where the muons are. So we need to know the position of them so that we can tell you what field the muons actually experienced. So we measure that with these two trackers. So here's a slice through the vacuum chamber. Your muons will be living on this green band here. And then the tracker detectors are over here. They look like this, the kind of straw modules that slide in. There's 8 of them that make up a station. And if you were here as a muon going around on this green line, what you see on the right-hand side are the detector modules over here. Now, you might decay at this point. You're going to decay to a lower momentum positron because you gave off some neutrinos as well. So this is then going to curl inwards in the magnetic field, go through the tracker, leave some hits, we make a track, and then we extrapolate this track backwards to the point where it's going radially tangent to the storage region. And this gives us some idea about where the beam is at any given time. So you can do that for all times. You take all the muons and scoop them up together, and you get a distribution that looks a little bit like this. So we call this the avocado plot because it looks like an avocado. And this is basically a slice through the beam. So this is the radial and the vertical distribution of the muons inside the storage ring. So we take this distribution here and we use that to weight the magnetic field. So this is a similar plot to the one I showed before, but just now with the muons on here as well. So we basically take the weighted average of the field with this distribution here, which gives us the right number for our denominator. Now this is the distribution over all time. What we're not seeing here are the beam oscillations, which are well known from beam dynamics, but we can take time slices, and you can make a video like this one here. This is real data, watching the beam swim backwards and forwards. I like to show this just because I find it kind of mesmerizing to watch the beam swimming in real time, ticking up in microseconds here. So these are important later for the precession frequency analysis, where the acceptance of the detector is different depending on where the beam is, and so these can couple into that analysis. Now, speaking of that analysis, that's the last ingredient we need. That's the numerator here. So we measure that using these calorimeters. So those decay positrons that I mentioned earlier, they're curling inwards, and we measure them with these 24 electromagnetic calorimeters that are all around the inside of the ring. So each one of these is an array of lead fluoride crystals. They look like this, kind of 1 inch by 1 inch by 6 inches long. And then we take an array of those. There's 6 by 9, making up 54 crystals. And then we read out the back of them with the silicon photomultipliers, which are digitized, and we read the full waveform. These are about the size of a quarter, right? And you stick them on the back of these so that you get, as well as energy and time information, you're also getting spatial information about where the positron hit inside the calorimeter. Okay, so I said we wanted to measure the spin, but I've just told you we're measuring decay positrons. So why are we doing that? Well, it turns out nature's been kind to us and encodes the spin information due to parity violation. So if you just imagine a muon at rest here, you have the highest energy positrons going back to back with the neutrinos, and then you can draw on your spin arrows. These guys are going to cancel each other out. And then what you find is that this highest energy positron is emitted in the same direction as the muon spin. So the idea is we just basically choose the highest energy decays, and they'll be pointing in the same direction as the spin. So we get information about how the spin is changing. Now, if you imagine then being sitting on a detector, this is what you would see in terms of the energy. So as the spin is pointing away from you, it rocks that way, and then the spin points back towards you, and the energy rocks back up here. Okay, so it's this oscillation back and forwards of the energy with time is what we measure. And the simplest way you could think of doing it would just be a cut and count, right? You put the threshold here, and you count the number in your black histogram here, and it's going to oscillate backwards and forwards. And the frequency at which it's oscillating is this spin precession frequency, omega A. So it's a cartoon picture, but it looks like this in real life. So this is all the data we have from run 1 combined. What you're seeing here is the plot wraps around. So it's a log scale. So this straight line is an exponential decay. So the decay is just going around here as the muons decay away. And on top of that, you're seeing this oscillation at omega A, right? This frequency that we want to measure. So we basically fit this and use that to extract the frequency. With our 8.2 billion positrons which go into this plot, the statistical uncertainty is 434. So at this point, that's dominant over all the systematics. And we have 6 different analyzers who've analyzed all this data. They all chose methods which had slightly different systematic sensitivities, and they all get consistent results for this value, and everything's in agreement. Okay, so in terms of systematics, there are just 3 main issues. We have the beam oscillations that I mentioned before, and we measure these with the tracker, and we've got beam dynamics models, so these end up being less than 40 parts per billion in total. Pile-up is another problem for us. This is where we have two low energy positrons which arrive at the same time. They shouldn't pass our threshold, but they do, because we mistook them for one high energy one. And so we correct this using the calorimeter data itself and ends up around 30 parts per billion. And then we also have a gain change problem where the beam comes in and there's a big flash of other particles that we don't store. And that all batters the calorimeters and they drop, the gain sags by 0.5%. They recover quickly and they're basically back to 1 by the time we start, but we do have a tiny little piece here which we need to worry about. And we have a dedicated laser calibration system which gets this systematic down to 10 ppb. So in total, everything's well under control, and this is only 56 ppb as the total. Right, so there are 3 ingredients. We've got them all. Are we quite done? Well, these were just the basics. Actually, we need these 6 small corrections to get our final result. And so these are the 3 ingredients I told you about before. We've gone from this simple picture to this more complicated one. We have the field calibration, which I mentioned earlier with the probe swapping. We have a clock blinding factor. And then on top of this, we have these beam dynamics effects. So these are well known and well understood. And they affect the measurement of the precession frequency, so they go in the numerator. And then we also have these transient magnetic fields, which are fields that are present when the muons are inside the ring, but aren't present on average when we're taking our NMR measurements. So we have to correct for those too. And you might get worried at this point and think, gosh, now you've got 6 numbers that you need to know to ppb level precision. But the experiment's been well designed, so the total correction of all these together is only 544 parts per billion, and we should compare that with a statistical error of 434. So we don't have to get anywhere near the same precision on these, right? We don't have to know these at the ppb level. Even if you just knew them to kind of 10%, then your uncertainty is going to be much, much smaller than anything we'd care about. That said, there's a huge effort to get them right, and it is where a large part of the collaboration's work goes, but I just don't have time to tell you about it today. So if you are interested in that, though, you can read some of the papers that we put out. So we have these 4 papers that were published at the same time as we released the result. There's the main summary letter. If you read any of the papers, you probably read this one. But we also have one that talks about the precession analysis. That's this PRD. We have one for the field. That's this one. And then we have one for those beam dynamics corrections, which is here. So if you're interested, please read these or corner me in a coffee break and we can talk more about them. Okay, so if you do look at the PRL and then skip through till you find the uncertainty table, this is what you're greeted with. The final uncertainty at the bottom here is 462 parts per billion. And the external constants that we use to translate from our measured ratio to A mu only contribute 25, so they're basically negligible. And the statistical error is 434 parts per billion. It dominates this result by a long way. The systematic error here is 157 in total. So this is a good number for us. It's nearly half the Brookhaven level of uncertainty. They had about 300. But we're not quite yet at the 100 part per billion goal. And so we've got a little bit more work to do. The largest corrections here come from these 2 well-known beam dynamics effects. These have been known for 40 or 50 years and haven't changed in that time. So we know how to calculate them. And then the statistical uncertainty at the moment, sorry, the systematic uncertainty is dominated by these 2 corrections here, which for technical reasons, so this is a kind of beam dynamics effect, and this is a field from the quadrupole storage magnets. So for technical reasons, these are basically going to improve a lot after this ROM1 analysis, and when we think we'll easily be able to get below our 100 part per billion goal. Okay, so we do the analysis blind, and we basically blind our clock frequency with some offset. Back in February, we got together as a collaboration. Here we are virtually meeting, and we had a vote and agreed to unblind. We were finished with the analysis. So it took us 3 years after taking the data to sort everything out. But we did then open the secret envelopes to be able to get our first result here. So just as a starting point, here's a plot with the standard model on it. This is the recommended value from the theory initiative. And here's the Brookhaven value, 3.7 sigma away. So with different people, a lot of different equipment and different beam, we found nothing that would change this Brookhaven result significantly from where it stood. So that stands as it always was. Our result comes in here. You notice we're like consistent with Brookhaven. The uncertainty is 15% smaller. And both of these are dominated by the statistical error. So that goes out to these ticks here with systematics after. There's good agreement between them, so it's safe to combine. And we do combine them here, and you end up with this experimental average, where the headline that we've all heard is 4.2 sigma, is the difference between now the experimental average and the standard model. Now, this result was released on the 7th of April at a webinar with 8,500 attendees. One of the nice things about being virtual is you can have a lot more people than you could fit in the Fermilab auditorium. And of course, the theory community was very quick off the mark. We're 6 weeks in and already sitting at 120 citations for this paper, almost like you guys knew it was coming. And as well as the theory community, we also have press from all over the world. So, you know, here we are on the front page of the New York Times and European press, Chinese and Indian press too. So just to kind of highlight this, and I hope you can all enjoy kind of physics' day in the sunshine there. Okay, so what's the outlook for G-2? Well, the future's looking really bright. There's a lot more data to come. Here we are. This is the data I've shown you today. There's a lot of white space on this plot, which you should be encouraged by. We took data in 2019 and 20, and we're analyzing this data right now. If things go according to plan and we don't have any unexpected surprises, then we're expecting to halve the uncertainty and release a new result next summer. And the systematics are on track for kind of 100 parts per billion at that point. We're still taking data. We're aiming for 20 times the total, and 1/4 of the current uncertainty is the final result here. And here's where we are as of today. We've got one more run after this, definitely, and we're hoping for a run 6, depending on how things shape up. So that's G-2. In the last few minutes here, I just wanted to highlight some other results coming out of this experiment and the Fermilab campus. So as well as AMU and the magnetic dipole moment, we also can search for an electric dipole moment. So as you know, the standard model electric dipole moment for the Muon is tiny. Any observation we see would be a sign of new physics. Now, the electron limit is much, much more stringent than the current limit for the Muon. And so the number here, it's 10 orders of magnitude difference between this. And this limit comes from the previous Brookhaven experiment. So naively, you'd expect this to scale as the ratio of the masses. So if lepton universality held, then it's pretty hopeless for a Muon limit here. But, you know, lepton universality is currently under threat, as we heard from Tulika's talk this morning. So maybe it's not such a crazy place to search for this. How this would show up in our experiment is instead of the precession plane being completely horizontal with the spin pointing around just in a horizontal plane, an EDM just tilts it ever so slightly. Oh, sorry, excuse me. Tilts it ever so slightly. So as well as an in-out oscillation, you also get an up-down oscillation. And this is out of phase with the normal G-2. So that's the up-down oscillation is the thing we search for. Eventually, for our final result, we're expecting to push the limit down 2 orders of magnitude from where the Brookhaven one ended up. And we're expecting to publish an intermediate result in around a year where we take a good stride towards that value. And there's 2 other searches we can do. So here's there's a standard model extension Lagrangian from Lorentz violating extension to it. This Lagrangian, if it was realized, would predict 2 signatures that we might be able to see. So we would see a difference in omega ray between mu plus and mu minus. So I've told you so far about this mu plus. We are hoping that there may be a window for us to take some mu minus data in 2022, 2023. This is not confirmed yet, but we're kind of angling to try and get in there. And then you'd also expect to see sidereal or annual variations in our measurements of omega ray. So we'll search for these, and we're expecting the sidereal variations to improve by a factor of 5, and the annual variation will be the first time we do this. And Brookhaven didn't run for long enough in the year to do an annual variation. Our runs at Fermilab are much longer, so we can do this. And then the final search that we're intending on doing here is, this was a new proposal that came out just last year. This was saying that interactions with muonphilic dark matter may also change this omega ray value. And so we can search for oscillations in this omega ray at different frequencies. And depending on the dark matter properties, it would be a different frequency here. So we'll search for that. I kind of highlight this one because it's new. We do have a rich source of data of these muons here with a precision measurement. So I encourage you all to think about other ways that we also might use this data to search for things and set more stringent limits. So the first results of these are kind of a year timescale as well. Okay, so then in my last just couple of minutes here, I want to also bring up where we're going after G-2. So at that point, mu2e will turn on at the Muon campus. So the mu2e experiment is searching for muon to electron conversion. This is charged lepton flavor violation in the presence of a nucleus. So it's basically this reaction here. The current limit comes from syndrome, and it's kind of 10 to the minus 13. So the final goal from U2E is to push this down by 4 orders of magnitude to get to 10 to the minus 17 and take a big chunk out of this, this parameter space. Now, the way it works, you basically have protons come into a target and with a technically challenging series of magnets, and that's where the real difficulty in the experiment comes. In building these magnets, you basically channel a high intensity beam of low energy muons that come round. You capture them on this aluminium target here, and then you sit and wait for them to basically watch them and look for electrons coming off them. You use this tracker in the calorimeter to look for monochromatic signal of 105 MeV electron, and it's coming through here. So that's the signal you search for. Now, normally in previous talks, you've just seen computer-generated images of these, but I just really want to highlight that this experiment is taking shape. Here's real pictures of it. Here's the experimental hall. Here's a production target that exists. Here's transport solenoids, and these now exist. Here's the first of the tracker panels coming off the assembly line. Everything's coming together here, and it's really getting built now. The first date is on the horizon. It's expected in 2024. Okay, so that's me done. Just to conclude, we measured AMU to 460 part per billion. We confirmed the Brookhaven result after 20 years. You can combine them and you end up at 4.2 sigma. It's only 6% of the final data sample, so the outlook for AMU is very positive. And there are other interesting results coming too for an EDM, CPT Lorentz violation, dark matter searches. And U2E is also on the way. This hardware is really coming together now. Thank you.
Okay, thanks a lot. Perfect timing. You can see that you're an expert on really measuring time and precision. Mm-hmm. So there were 2 questions on the chat. So let me start with the second one. So somebody is asking, why do you use positive muon beam instead of a negative muon?
You can make more muons that way.
Okay.
In terms of coming from the target, you just end up with slightly more muons that way. It's kind of a factor of 2/3 if you go to the negative ones. And there's also some challenges as well where you need a slightly better vacuum if you use negative muons, because the decay positrons can also get trapped inside the field too. So you'd need a better vacuum to operate our electrostatic quadrupoles. So it's just easier. And if you think CPT holds, then it should be the same.
Yes. Okay, good. And then, of course, there was a question about the theoretical prediction. So I know that there will be a talk this afternoon, right, and dedicated to this lattice computation. Nonetheless, maybe you can comment briefly. So here on that slide, actually, you are reporting this 4.2 sigma discrepancy. But of course, you're certainly aware that there is also recent lattice computation that claim only 1.6 sigma, right? So I don't know. Do you want to comment on that?
Yeah, okay. So this is this is a question we get asked a lot, right? And so I'll preface this saying this is an experimental's misunderstanding of a theoretical thing. So just the background is on April 7th. This is the same day as our result came out. This was published. This BMW collaboration's result is the first of its kind that's lattice QCD that's sub-precision. And the thing is, this is very impressive progress, right? To go from, is the first one you can see they made huge stride in terms of the precision of this, but it's a difficult problem. And there's a tension here, right? Between this, these guys have to agree, right? They're 2 calculations of the same thing. So we're either saying that this analyticity and the optical theorem is wrong, or the data is horribly wrong here, or there's a problem with the way this one's come. So I think what I just quote is the final sentence of this paper, right, from this BMW result, which says this finding should be confirmed or refuted by other studies using different discretizations of QCD. And those investigations are underway. And the theory initiative decided that it wasn't ready for them to include this yet. They're waiting for these investigations to conclude. And then if they turn around and say, we think we should be comparing to this number instead, then we stop comparing to this white paper, it'll move and we'll compare to a different one. And so at the moment, we're just, as experiment, are watching closely to see how it pans out, and we're making the most precise measurement we can.
Okay, makes sense. Thanks a lot.
And I believe Hartmut will also talk a little about this in his talk as well. So we can presumably continue the discussion there.
Good. So we still have 1 or 2 more minutes. Let's say I see another question. So for the future mu to E experiment, what was the motivation for this choice of this nucleus target rather than other element?
So it's, oh geez, now I have to remember this. I think it's driven mostly by the capture lifetime. So different targets can also have different effects on the rate. So, you know, if you were lucky and the rate was quite high, then you could imagine swapping out targets and learning about what the BSM physics might be behind it. And so there is some choice in the target, but I think here it's balancing the density to stop the muons versus the capture efficiency. So your muons get captured on the nucleus and disappear before they have a chance to convert. So you need that to be long enough. And I think that's why the aluminium one was chosen over, say, titanium or some other options.
Sounds good. Okay. Is there any other question, comments? I don't see it. Okay, so maybe it's time to thank you again, James. I mean, this fantastic result, right? And we are looking forward to also the measurement of EDMs, right? That would be fantastic.